Hey friends, welcome to my channel, and in this video I am going to entertain you by the Pauson-khand reaction. I am saying entertain you because this reaction is very interesting. And first of all, the Pauson-khand reaction is the reaction of these three components, this alkyne, this alkene and this carbon monoxide molecule to give you this cyclopentanone. Okay, so this is a very simple reaction. As you can see, only a cobalt catalyst is used in this reaction, and out of this you can get this very important molecule. So you frequently talk about retrosynthesis, that I should make a video on retrosynthesis, but I have not much time because the making a video on retrosynthesis is very time consuming, and retrosynthesis is not a very important topic for CSIR exam also, because they didn't give you the question straightforward from the retrosynthesis. But you can see this is a good example of concept of retrosynthesis, because whenever you meet a circumstance where you have to make a cyclopentanone, you will always think about this Pauson-khand reaction, because it is the best way to make a cyclopentanone. And you can see you just have to be with you these three components, this alkyne, this alkene and this carbon monoxide molecule. You treat them in presence of this cobalt catalyst and you will get this cyclopentanone. But the reaction, as it seems very simple, the mechanism of the reaction when you try to write is very much complicated. And in the book Claydon, the old book of Claydon, it is given, but in the new book it is not given. And at the discussion where they discuss this mechanism, they itself write that only very few chemists can write this mechanism without looking into the book. So by these statements itself you can understand how complicated the reaction mechanism is. But I promise you that after watching this video you will be able to write this mechanism by your own, and I will try my best to make this video very simple and to make you understand. So let start the reaction mechanism. So this before discussing this reaction mechanism, you should have a basic concept of organometallic chemistry, because the reactions like reductive elimination, then migratory insertion, alpha migration, beta migration, these concepts are needed for this reaction. And if you are preparing for CSIR exam, I suppose that you know these things. So the catalyst here used is this cobalt catalyst, cobalt octacarbonyl. So the structure of cobalt octacarbonyl is this, and by this video I will also discuss the count of electron, that is how to count electron for a organometallic compound. So this is the catalyst, CO2, CO8. And if you count electron for them, I will always prefer neutral electron count method, because it is simple. And by this method, this cobalt has 9 electron, then your each of these three carbonyl has 2 electrons, so 2 into 3 equal to 6. And this bridging carbonyl contribute 1 electron for each cobalt, so 1 and here 1. In this cobalt also it is 1 and 1, so you have two, total of 2. And then this cobalt cobalt bond has 1 electron, so total of 9 plus 6 plus 2 plus 1, that is 18 electrons. So you can see this is a 18 electron compound. Now a 18 electron compound spontaneously cannot undergo any addition reaction or insertion reaction, because it is already stabilized. And if it take another ligand, it will be unstable, because that will lead a 20 electron species. So before reaction, it has to lose its one of the carbonyl groups. Okay, so it will first lose these two bridging carbonyl ligands, that will give you this. Now you can see both of these cobalt centers are 16 electron species, because cobalt 9, then 9 and 1 10, and this 6, so 16 electron species. Each of this cobalt is now 16 electron. So after that, what can happen? You have alkyne in your medium. So your alkyne, let's say this is your alkyne, and it can bind to this cobalt like this. I will not push arrow. You can just simply understand the alkyne will bind like this. So each from each center there will be two bonds to this cobalt, because that will lead to it now a 18 electron species, because you have 16 and now each of these bond contribute one electron. So one here and one here and one here and one here. So one electron contribute for each, or for this center. This actually each bond contains two electron, but when you consider this alkyl bond to a metal, you take one electron in the neutral electron count method. So you have now this is 18 electron complex. Now you can write this particular complex in a more simplified way like this. So this is your cobalt cobalt bond, and you have these three ligands over here. Now your alkyne, you may write this. So you have this R groups here. Now here will be these two bonds. Okay. So it implies that this alkyne is the backward of this board. Okay, so this is another representation of the same molecule. So these two are same. And why I am representing it like this? Because it looks very simple. It represents the symmetry of this particular molecule, particular compound. Now, as it is a symmetric molecule, uh, all both cobalts are same, and so it is 18 electron with respect to both cobalt, and further addition of ligands can only occur if it lose another ligand, and one of the cobalt can do this because both are symmetrical. So let's say this carbonyl is now removed. Okay, so I will write another step. So now you will have this. So here you have three. So here you have this three carbonyl, but now there is a vacant position, and this alkyne is same. It is here. So R and here R. Now this vacant position, it is now 16 electron, and at this vacant position the alkene can insert. So this I am taking simple ethylene molecule, because I will not I'm not mm, introducing complexity to this already complex mechanism. So, and one thing I would like to say is that please write this mechanism with me on a paper, otherwise you will not get it. Okay, so now this alkyne can insert, can add here like this. Okay, so that will lead to it a 18 electron species, because it contributes 2 electrons. Now what can happen next is that if you know the Hake reaction or other that type of reaction, in this type of situation a beta migration occurs. So this is a beta migration step, because this is alpha, this is beta, this group is migrating to the beta carbon, so this is called beta migration. And by this beta migration you will get this intermediate. So I am omitting these ligands because these are remaining same throughout the reaction. I will write only this part. So now you can see this is 1 2 3 4 5. This will become a 5-membered ring. So I can write a 5-membered ring like this. Okay, and you have this R group just adjacent carbon to the cobalt. So here you have the R group, and this alkene part is actually this is your alkene. Now another, the above part is same. So you have this, and you can see this, there is a bond between this carbon and this carbon. So you have to identify these two. So this is your one carbon and this is your one carbon. So this bond is actually this. Okay, so you can see this is bond. So out of this beta migration step you will get this, and you have 2 carbonyl here and 3 carbonyls here. You may not write it because these are remaining same throughout the reaction. Now after that what can happen? So you can see now it is again, if you count the electrons, it has cobalt has 9 electron, and then these 2 for 2 into 2 4, and then 1 1 1 each, so 3. So it is 16 electron again. so it can add another carbonyl group here. So it will add simply another carbonyl to give it a 18 electron complex. So it is 18 electron throughout the reaction because no change is occurring at this particular center. Now it is 18 electron. So I can write this carbonyl group like this. Okay, so this is the representation of the carbonyl group when I open the structure. Now what can happen? These can migrate here, and this is called alpha migration. Previously it was beta migration, now it is alpha migration because it is the alpha carbon. With the carbon which is bound to the metal, it is called alpha. The next carbon is called beta. So it is alpha, and this center is migrating to this alpha center, so it is called alpha migration. And you can see after this it will form 1, 2, 3, 4, 5, 6. Now it will form a 6-membered ring. So you can write this 6-membered ring here. Okay, and you have this R group here, this. Now you have two carbonyl groups here, and this carbonyl now becomes keto. Okay, and here you have another R group. Now after that what can happen? So this is the, so you can again count the electron here, and if you count it will be 16 electron because it has 9 electron for cobalt itself, then 4 electron from these two groups, 4, and then 1, 2, 3. So again it is 16 electron, and it can put another carbonyl group. Okay, so by these two steps, two carbonyl groups are added, and you get this. Now you can see whenever you have a situation where you have a metal and two bonds like this R, and here you have a carbonyl, like anything like this, so these can undergo a reaction called reductive elimination. That is, this group comes here. You can think a mechanism like this. Same reaction what happens for a ester hydrolysis or that type of reaction, but it is different. But you can draw an analogy with that. So if you draw like this, you will get this metal plus this RCOR. So this type of reaction is, so basically what is going on here is that this group and this group together leaves as this, and you have your metal. So this step is called reductive elimination, and in organometallic chemistry you will encounter this type of reaction very frequently. So here again you can see this group and this group, they are same as before, so it can undergo a reductive elimination reaction. And if it undergoes a reductive elimination, what you will get? You will get, so you can see this is 1, so you can number 1, 2, 3, 4, 5. So if these two center binds, you will get a 5-membered ring. So that ring is nothing but this. So this is your 5-membered ring, and you can see as I numbered, so this is carbon 1 and it is bound with this R group. Okay, and you have this two carbon here, you have another R group, this R. So 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. And now you can see there is a 3-membered ring. So when it undergoes migration, what will happen? So this bond comes here and it push here. So you will have a situation like this. Here you have cobalt, and with this cobalt, so with this cobalt you have three groups, three carbonyl groups, and another cobalt here which has another three carbonyl groups. Okay, now you can see this is 18 electron because 9 plus 6 plus 3, so it is 18 electron. But this is again 9 plus 6 plus 1, and it is 16 electron. But that doesn't matter, it can take up another carbonyl, so it becomes 18 electron also. It doesn't matter. So out of this step, this step is very important. You can see this bond, this particular bond and this bond, they undergo a reductive elimination reaction, and if you number it, if you draw in your paper, you will find that a 5-membered ring is forming, and this 3-membered ring is nothing but this one. So if you mark, this is your this 3-membered ring. You can see this is a 3-membered ring here. So this is this same 3-membered ring which involves a cobalt center in it, and this cobalt, so this cobalt is this cobalt, and this is this. So you get this. Now again a reductive elimination can occur, and that is this. So out of this you will get this compound, and now you get back your CO2, CO6, but it can later take up to cobalt, to carbonyl to form CO2, CO8, which is your starting material. So it is catalyst because it is regenerated after the reaction, and you will get this product. So this reaction looks very complicated, and you have to practice fewer times to get it fully. But one clue for this reaction is that whenever you are doing this reaction, you can see throughout the reaction only one, after the alkyne insertion, only one cobalt center is undergoing reaction, other cobalt center is remaining same as it is until the last step where this reductive elimination occurs. So before this last step, only one cobalt center you have to focus, and all the reaction sequence I discussed you have to do, and then after the last step you have to do this reductive elimination step, and out of this you will get this cyclopentanone. So this reaction is very important, and it is the full mechanism of the reaction. Now I will tell you about the regioselectivity of the reaction. So actually I can tell you the regioselectivity of the reaction, but that will make the video very long, and I am not going to do that. I will discuss some more examples of the Pauson-khand reaction in the next video, and the examples which came in CSIR exam also, the stereoselectivity and regioselectivity. So for that moment, if you like the video, then give a thumbs up, and also share this video with your friends, and thank you for watching.